Yeah. Let me introduce the speaker. Okay, so welcome everyone to this week's ICTS String seminar. We are pleased to have Cumrun Vafa from Harvard University, who has graciously agreed to give us a talk on his recent work. Over to you, Cumrun.
Okay, so thank you very much for the invitation. It's a great pleasure to give a talk here. So let me see if you see the full screen now.
Yeah.
Great. So I'm going to talk about geometric obstruction to scale separation. This is based on a number of a few papers. One is the paper with Collins, Jeffries, Chu, Yao, which appeared in January, on upper bounds in dimension gaps of CFTs. And the other one is a paper with Severin Lust and Max Wiesner and Kai Chu, again, in April, on holography and the KKLT scenario. So I'll be talking about these two. I will refer to some aspects of some ongoing work with Jeffries, Montero, and Valenzuela as well in this context. So if you look at homogeneous solutions in string theory, there are of three types. Homogeneous in terms of, space-time. There are three types that you can imagine. We can imagine, except for my spelling, I guess, Minkowski, ADS, and de Sitter. The zero, negative, and positive cosmological constant, which schematically would, if you have viewed them as potentials as a function of scalar fields, abstractly, it will look something like this. The ADS will have some minimum and negative value. This there will be something positive, and the zero case, the Minkowski's case, will have zero potential. So in principle, we can obtain these by string compactifications. So Minkowski times an internal space. So we basically have some kind of an internal space appended to the homogeneous space that we would be interested in. And we try to construct these within a string theory landscape. Currently, there is no reliable de Sitter construction in string theory, and we don't know if it really exists or not. Even if it exists, we don't think it would be stable de Sitter. At best, it would be metastable, and we still don't know even if sufficiently stable, metastable, sufficiently stable, now as long-lived metastable de Sitter also exists or not. So these are still being debated, and we don't really know. However, for Minkowski and ADS, the situation is much better. In the Minkowski case, we have many examples where we can construct them famously in the context of supersymmetric compactifications, for example, of Calabi-Yau manifolds. We have a plethora of examples with Minkowski space emerging with strong control about the aspects of light degrees of freedom and effective field theory that emerges. Now, in this context, for example, in the Minkowski space, there is no scale associated to Minkowski. It's zero cosmological constant, and related to that, the scale of the internal manifold can typically vary from whatever we want to whatever large or small we may choose. So usually it's a free parameter. So there's no scale obstruction in this case. There's no scale because there cannot be any correlation with scale because Minkowski has no scale. In the context of the ADS and de Sitter, however, there's a length scale associated to them because of the curvature of ADS or de Sitter. So in the case of the ADS, even though we have many solutions, the length scale associated to ADS and the length scale associated to the internal manifold do not seem to be independent. Now, let me be a bit more careful about what do I mean by these length scale. The length scale of ADS is kind of clear because there's only one curvature that we have, and because of homogeneity, so the length of ADS is clear. What do I mean by the length scale associated to K? Well, this K could have different components. So roughly speaking, I mean the diameter of the space. In other words, you can have different pieces that have different sizes, but you can view this L of K roughly as the diameter of this manifold. That's what I mean here by L of K. So for example, if there's a piece of K which is small, another piece might be large, the large one which dominates, which gives you what LK is. Now, there is a distance conjecture in the context of the swampland program. The distance conjecture tells you that if you go at large distances in field space, you always get light degrees of freedom, leading to a dual description. So basically, this conjecture says that there's a mass of light states that emerges in this way at large distances in field space, goes exponentially down with the distance in field space, like e to the minus some constant times the web of the field space, field, for example, scalar field. And this is basically, in some sense, the duality conjecture. That is, it's the same statement as saying that there's light states that emerge at far enough values of these field spaces to basically play the role of dual degrees of freedom to give you a dual description after all. So distance or duality conjecture is basically related to the existence of dualities in string theory. Now, in the context of ADS, this distance can be also applied. In this context, the metric on the ADS is a field, and you can look at the distance in field space associated to the metric on ADS. And in that case, the log of the cosmological constant plays the role of the field, and therefore that would be related to the corresponding distance. So that corresponding scalar field that we evaluate. So if you make the ADS to be big, you expect to get some tower of light states, because in that case, the distance is going to be large and you get some tower of light states. So if you trace it through the fact that log lambda is a field and e to some power constant times log lambda plays the role of the mass, it just tells you that the relevant mass is scaled with some power of LADS. And this basically gives you a relation that the length scale in the internal space is not decoupled from the length scale in ADS, and there's some parameter A, which is of order 1. So that is the...
I have a question.
Yes.
Yeah. So typically this ADS radius is quantized, right?
Yes, correct. But metric is not, of course.
Metric is not, but the moduli space, there's a continuous moduli space. So you cannot
vary that. So that's correct. So what you're referring to is that the moduli space is discrete in this case.
That's right.
But the metric, you can measure the metric in field space regardless. In other words, you have a potential in the field space in the metric. So if you fix the flux, and as a function of the metric, you can say what value of the metric you go to get the solution. And if you change the flux, the metric moves more or less. So the distance I'm talking about is the distance in metric space.
I see. The fact that you have to also change the flux.
Yes, you can also, I should be more precise. You should also include the flux distance. So it's at least given by the distance in the metric space.
I see.
So but there is a notion in which you can do it, and it's the same scale, basically.
Okay, thank you.
You're welcome. So
is there some understanding of, is there some understanding of this conjecture from the point of view of the CFT bootstrap? If I try to define
yes, I'm coming to that. That's a very good question. That's exactly where I'm heading, actually.
Okay.
I have a question.
Yes.
So this exponential of, essentially you're saying that this L to the A ADS comes from exponential of log A times log, exponential of A log L, right?
So basically it says mass goes like powers of LK. In other words, so the mass, so let me say it better. So if you take K to be big, you get a KK scale, whose masses go like 1 over L. Cosmological constant goes like, the lambda goes like 1 over L squared, L of ADS squared. So I'm saying that the masses should be of the power of lambda, which is itself, log of it is the field, because e to the log of the field is like lambda itself. So powers of lambda would be related to the mass scales, and this is basically captured by such a relation.
Okay.
Is that clear? Yes. So and this is of course the case in all the examples we know in string theory. That is, in all the examples we know, whenever you make ADS big, you always make K big. In some sense, it's a bit of a misnomer to call this, for example, ADS CFT correspondence. It's ADS times some other space. You cannot forget the fact that this other space has the same scale as ADS. And this is basically captured by this fact. So the ADS is not by itself meaningful. It's ADS times something. It's always with something. And the conjecture that in
So
fact
this is related to the fact that ADS D cross ST, for instance, have the same radius. For instance, ADS cross S5 have the same radius.
exactly. That's a good example. ADS 3 times S3, for example, times T4 or K3. The T4 or K3 could have a fixed scale, but when you make ADS3 big, at least one part of the internal space, like in this case, the S3 radius, gets as big as the ADS radius. In that case, the radius are equal. So A is 1 in that case, in this parameter.
Yeah. Okay, thanks.
So the statement, in fact, in all the reliable examples we have in string theory, A is actually equal to 1. So a strong form of this conjecture is that there's always equal to 1.
Cumrun, sorry to interrupt, but how much of this relies on supersymmetry, some amount of supersymmetry being preserved?
Yes. So the statement of the distance conjecture is more general than the supersymmetric one. Of course, we have evidence for it mostly because of supersymmetric examples. But the statement could be made sense and has been made sense in general. For example, in non-supersymmetric vacuums like O16 cross O16, if you go to the weak string coupling, you still get a tower of light states. So this statement is not really driven by supersymmetry, we think. But again, it's the duality. It's really duality. If we believe there's always duality regardless of whether it's supersymmetric or not, this is basically the content of the statement. In this case, there should be a dual description emerging, and in this case, it relates to this type.
I see. Okay. Thanks.
Yeah. So this comes to the question that was asked, about the connection with a CFT dual. So in the CFT dual for this ADS, there's a correspondence with the dimension of the operator, which is the mass times the mass of the states in the bulk times the length scale associated with ADS gives you the scaling dimension of operators in the dual CFT that we get. So in this case, this means that the dimension of the operators, if you put LK there, gives like L of ADS to the power of 1 minus A. So if A is 1, that means the dimensions are typically of order 1. In other words, it starts with order 1, and when you take the KK towers to be bigger and lower, you can go higher and higher. This basically tells you that you have no gap in the spectrum of CFT, that you start getting the tower of states that you would have. A being bigger than 1 simply means that you could have some light states, like dimension states potentially. That would be A bigger than 1. But if A is less than 1, that means you could have in principle a big gap. Because if A is less than 1, you see that from this picture, if you make the L of ADS to be big, then you can make the dimensions here also big. So therefore, then you will get a big gap in this situation. So the conjecture is that you never get a big gap in these situations. Now, so that is related to, in particular, to the bootstrap potential verification or falsification. Namely, can you construct conformal field theories which have a big gap in the dimension of the low-lying operators? That's the question. How much can you push the gap up? Now, more precisely, this relates to the conformal field theories which do have holographic duals, because here the discussion here is in the context of holographic theories. Now, why is this an important question? Well, it's certainly interesting from the point of view of CFT to know whether or not this is possible for a better understanding of the space of CFTs, but actually it's also crucial for understanding de Sitter space, because if indeed you could have a scale separated situation, like if you could really make this internal manifold to have a scale independent of ADS, or at least very mildly related to the ADS length scale, then you can imagine having a situation where the cosmological constant of ADS is very close to 0, but the internal space is not too big. And then you can imagine slight perturbation of it by breaking supersymmetry could push it up to a de Sitter vacuum. So having a scale separated ADS would be a first step, or would be a first step towards constructing a de Sitter vacuum in string theory. So this is a crucial question also for de Sitter, even though the way it sounds like it's coming from the ADS question. So for this, this is an important question from many different perspectives. Now, what do we know about the dimension gaps in CFTs? Well, if you're in dimension d space-time in CFT, then the dimension of operators being less than or equal to d, we call these operators relevant or marginal. Dimensions bigger than d, we call them irrelevant. Now, no CFT is
Cumrun, I
known.
have a question.
Yes.
So if the K manifold, if the extra manifold is very large, wouldn't that mean that the KK modes will be extremely light, which are ruled out by experiments?
We are not talking about our universe necessarily. We're not talking, our universe is certainly not ADS.
No, even if it was DS. Okay, fine. Okay, good.
Yeah, for the DS it to be exactly ruled out, and that's related to the fact that you don't want the internal one to be too big if you want to get the de Sitter out. Exactly. That's the whole point. So in other words, if you want to use this as a springboard to construct de Sitter vacua, you better make sure that this internal manifold is not too big. Exactly.
Yeah.
So that's why it's important to understand whether or not we can approach zero cosmological constant with the relatively fixed size for the internal space, or more under control than the one we are naively getting. Now, no CFT is known with no low-lying conformal operators, and in fact, the biggest known gap is for two-dimensional CFT, and this is the monstrous moonshine construction, which gives you the first non-zero operator of dimension 4 if you look at spin zero operators. More precisely here, I'm talking about the symmetric version of moonshine, and if you look at the spin zero operators, you can have a situation where there is no relevant or marginal operators, but you cannot make them arbitrarily large. In fact, 4 is all you can get. And this is the theory which has, the biggest exceptional group as a symmetry group. So clearly we have done something super exceptional in this particular situation. And despite a huge amount of effort in trying to construct other conformal field theories with a bigger gap than this, all attempts have failed. In fact, Witten had a conjecture that you can make these conformal field theories with bigger and bigger gaps, even though there hasn't been really a proof that this cannot be possible. It hasn't been constructed, and there are some no-go theorems. In fact, in a recent paper, Dupay showed that at least 70% of these cannot be done, based on using the theory from elliptic modular forms and aspects of that theory. But the main point here is that we don't have examples, and it's possibly that they don't exist at all. But we may say that, okay, so maybe we have a few low-lying operators, like in the case of Calabi-Yau compactifications in the type 2 strings. We might have massless states. That would be light states. That would be analog of relevant marginal operators, for example. But then you can still make the internal manifold to be very small, so therefore you have a huge gap after that. So the question would be, can you make the KK scale to be very large compared to the low-lying states? So in other words, if we don't care whether we can have no low-lying operator, but just whether or not we can have a big gap after that is a more relevant question for us. So this is the question we want to ask, not that there is no relevant or irrelevant operator, but could it be that the CFT has a few low-lying operators, but with a large gap after that? That would be what we are aiming for. I hope that's clear. So we want to see if there is such a situation possible. None is known. None of this type is known. So now we go and ask if this is possible using holography. In other words, can we make the KK tower be made heavy?
So can I ask a question, Cumrun?
Yes.
The problem you described previously, of course, none is known, but to find an explicit CFT would be tantamount to solving the cosmological constant problem, right? Because we would have something which didn't have supersymmetry, and there was a small non-zero cosmological constant. So it's true that none is known, but of course, one would expect it would be hard to find it explicitly. But isn't it also true that there is also no known obstruction to solving the bootstrap? If one just starts with a large gap and tries to solve the bootstrap equations, there is no known obstruction to solving that.
So I don't know if I agree with you whether or not this is as hard as solving the cosmological constant problem. So I wouldn't a priori, for example, within conjecture that these exist and people try to construct it. They could have been a counterexample from the get-go, right? It is not as hard as you are stating it. I'm not talking about de Sitter space here. I'm talking about ADS, and I'm not talking about non-supersymmetry. I'm talking about supersymmetric. So take a supersymmetric CFT, for example. Can you make the dimensions large? This should be approachable, and we have 0 examples.
Okay, I agree. We have 0 examples, but would you also agree there's no known obstruction to solving?
There's no known obstructions. Well, there are some obstructions in the case I told you, for example, for Witten case. People did find obstructions. For 70% of the case, topological modular forms were used by Dupay and company to give obstruction to 70% of the cases. He couldn't cover all the cases. They couldn't cover all the cases, but large of them were ruled out. So it wasn't known until last fall. So yes, you're right that we don't have an obstruction yet, but it doesn't mean that means everything is good to go.
Okay, thank you.
Yes, but here, in fact, my point here is exactly give evidence that it's not good to go. I'm going to provide evidence that the most obvious attempts to get this would fail, and would fail for reasons which are not obvious why. So that's the point of my talk here, to try to explain why sometimes the things that you think should be possible, in fact, don't look like they're possible, and why geometry seems to not allow that to happen.
But that would be consistent with the conformal field theory picture, right? I mean,
Yes,
the
yes.
failure would be...
Exactly. Yeah. So conformal field theory does not seem to get it. We haven't developed the bootstrap method sufficiently far, in my opinion, to be able to get to a deeper understanding of why this is difficult to get or why it's impossible to get. But no example is known, and in principle, it shouldn't have been that difficult to get some, especially in the supersymmetric case or in 2D, where we know a huge amount of information about 2D CFTs. So let me try to build up. Let me try to go the other way. Let's try to actually do this in a holographic setup. Try to find a big gap by trying to push the KK scale up, namely trying to take the manifold, make it small. So we want to focus, if you want to focus on large tower of KK modes, we might as well talk about massive spin 2 operators, because the KK mode, there's the Laplacian, if you look at it for the scalars, among them would be corresponding to the massive modes of the graviton in the ADS context. So if you look at it from the holography perspective, you're looking for a massive spin 2 dual operator. So therefore, the question of whether or not we can have the KK tower to be heavy is the same thing as asking, what is the mass of the first spin 2 operator, or what is the dimension of the first spin 2 operator? We need to find first non-zero eigenvalue for the Laplacian, and if the eigenvalue of the Laplacian is lambda, then the corresponding dimension of the operator will relate to it by a formula like this in dimension d, where a is some order 1 number, depending on which model, which particular theory we're considering. Now, we will consider holographic cases where branes probe singularities of internal manifolds. So you imagine having a brane approaching a singularity of some manifold and giving rise to conformal field theory. A large number of conformal field theories that we know of arise in this way in the holographic context. And this leads to a geometry which is ADS times K, where K is an Einstein manifold, and together with suitable flux, which is replacing of this brane by the corresponding flux in the dual holographic setup. Now, the Einstein manifold will have more detailed properties depending on which supersymmetric setup would be. It could be, for example, Sasaki-Einstein manifold or Kähler-Einstein manifold or whatnot, depending on what is the precise case we are doing. But generally speaking, all of them will be an Einstein manifold satisfying an equation of the form the Ricci curvature is proportional to the metric with some proportionality constant, and we will scale the ADS so that the length scale associated to ADS is given by the formula. So we can always assume the Ricci curvature is n-1 times the Gij. Here, basically, I've used this to set the radius of the round sphere to be 1 in this normalization. Basically, this will give you that curvature. Okay. So let's consider an example. Many of these examples of holography start with some sphere as the internal space, like ADS 5 times S5, or ADS 3 times S3, or ADS 7 times S4. So it starts with a sphere. Naively, it seems it should be possible to have a very large first eigenvalue by a simple trick. You take the sphere and you consider arbitrary quotients, where G is the discrete subgroup of SOM plus 1. So you take a bigger and bigger quotients, and what happens is that the corresponding volume of this space goes down by the order of the group. And if the volume goes down, you would think that the length scale associated with that sphere also goes down by 1 over the order of the group to the 1 over nth power. So as the order of the discrete group that you're modeling out goes to infinity, you would expect that the corresponding the length associated to the internal space to go to 0, and therefore the first eigenvalue, which should go like 1 over the length scale of k, should go to infinity. That was easy. That's a nice counterexample. If we can do this, so it doesn't sound like there's a big issue here. We just take this and squeeze the sphere to nothing, basically, by quotienting out this way, that way, or some combinations, complicated way, to squeeze it as much as possible. And since the curvature doesn't change, this doesn't change the ADS scale, but it does change the radius of the internal space, and we will be getting a larger and larger first eigenvalue. Sounds like a good strategy. Well, let's try it. So suppose you're looking at the sphere and you conjugate out by Zn and take n to infinity. Well, in this way, you actually make these distances very small, but as you see, the diameter of this space has not gotten any smaller because the distance from the north to south pole has not changed by this quotient, even if you take n to infinity. So that means that even though some of the KK modes have been pushed up, namely the KK modes corresponding to wavelengths going from one side to here, but the corresponding modes going from the north to south pole have not gotten any higher in mass. Now, one can try to be a little more fancy and mod out by exchanging the north and south pole, like dihedral groups that you can imagine, and this will cut the diameter by half, but doesn't do much better than that. So the naive attempt, at least for the sphere, seems to be failing to do this. But maybe we are not being creative. Maybe higher dimensional spheres are different. Maybe we can do more exotic groups and so on. How about those? It turns out none of them work. So let's consider, for example, the 3-sphere.
Cumrun, I have a question.
Yes.
Suppose you do the modding also on the equatorial plane or equatorial diameter. I mean, the modding that you're doing on the North Pole, South Pole, suppose you do it along the equator also, then what happens?
This is, well, I don't understand what you mean by along the equator. This modding,
I mean, along the equator in the sense that along the equator, you can choose another North Pole and South Pole, say West Pole and East Pole.
No, but it should fit to a group. The subgroups of, for example, SO3 are ADE, classified by ADE. So you can use A subgroup or D subgroup or E subgroup. There's nothing else. The A subgroup is the cyclic group that I just talked about. The dihedral group is just the one I told you up to the north and south exchange. And then there's a few exceptional ones. That's it. No,
yeah, what I'm saying is, instead of taking a subgroup of SON, which, as you have said, you have modded out by that particular subgroup, which partitions the sphere along the latitudes, or rather the longitudes. What happens if you now consider an additional subgroup and mod out?
The point is that if you choose your additional subgroup, combine it with these other groups, forms another group, right?
Yeah.
Okay.
You have to take
I'm just saying that the total group is either A or D or E. ADE. So there's no other group. You cannot get any other group other than this list. It's either the cyclic group, the dihedral group, or this exceptional groups.
Can't you have product subgroups?
You cannot have product subgroups. All the subgroups of SO3 are ADE. You're talking about subgroups of SO3, right?
Yeah.
That's it. There's nothing else. If in other words, if you think, like, for example, if you choose a Z3 and a Z2, like their product, but they actually form another one, which is Z6. So I'm talking about that. It includes that. So there's nothing else you can do. So the full thing forms ADE.
But you can have Z3 along one axis and Z2 along the
no. They won't form a group. They won't form a group. I'm just trying to say that you would have been able to form a group that doesn't form. In other words, the only subgroups we have of SO3 are ADE. That's the classification. That's precisely why the naive intuition fails. What you're saying is exactly what naively one would have thought. The naive intuition would have said that, oh, you do the same thing on the other direction and the other direction and the other direction, you squeeze it down to zero size. That's what doesn't work. So this is the point I'm trying to make here, that naively we would have thought it's possible, but it's not. So for the case of the three sphere, if you do this, you could think that this might be because I'm doing low dimension, or let's go higher dimension, three sphere and others. You do this, and again, you find that there's a bound. In fact, the first eigenvalue you find is bounded by 3. That's the case for the round sphere. And if you push it on the lower side by 3, and if you push the sphere to be smaller and smaller, the biggest you can make the first eigenvalue is 168. So said differently, the diameter of the three sphere starts with pi. And when you do this quotient thing, the smallest you can make the diameter is go down to 0.32, which would correspond to this 168. This gives you the first eigenvalue of this, the corresponding first eigenvalue for the spin 2 operator to be between 3 and 14. Now, you could ask which group did this, and it turns out that the group that achieved this is icosahedral subgroup of the symmetry group. So the symmetry group of S3 is SO4, which you can think of SU2 left times SU2 right. You can take a diagonal SU2 inside it, and if you take an icosahedral subgroup inside that product, it turns out to give you the best one. So the exceptional one, the icosahedral one, which is the exceptional subgroup embedded in this way, gives you the biggest gap you can achieve. Not the naive cyclic one, which is infinite order. That does not give you the highest gap. You can do the same thing for the 5 sphere, and this is the SO6 subgroups again. You will find that there's a bound. In this case, you can push the diameter from pi only to 0.96, not even to 0.32. And for the higher sphere, it's even you can push it a little higher to 0.84, and the dimensions, as you can see, the gap gets smaller from 3.5 to 8, goes from 3.5 to 5, and so on. So as you can see that you're not achieving a big gap, and there is a bound. And all these examples is actually somehow related to the exceptional subgroups here that will achieve the best one, the highest one gap. Now, in fact, this is true not, so let me just emphasize this. I'm not assuming supersymmetry. I'm allowing for this group to break supersymmetry. I'm also not imposing that it should be fixed point free. This group could have fixed points, which will give you an additional massless modes coming from the fixed points, which I'm ignoring altogether. I'm only talking about the bulk states coming from the quotienting of the states that we already have in the unquotiented theory. So the statement is that this statement is robust. It doesn't care about supersymmetry. It doesn't care about whether there's a fixed point. In fact, this statement can be done not only for the spheres that can be used for the landscape, it's true for any n-dimensional sphere. For any n-dimensional sphere, you can show, using group theory, using subgroups of SON, you can show that the diameter cannot be made too small. There's a bound, namely, if you fix n, there is a lower bound, which depends on n, the dimension of the space. By the way, how much time do I have? I'm not sure if I'm on time.
We typically go on for 1.5 hours, so I think you're good. But please feel 1.5 hours.
Oh, 1.5. Okay, good. So
But sometimes we also go beyond that. So it's really up to you.
I'm not going to go beyond 1.5. So I just was worried because I think I would not I probably won't finish it within an hour.
That's completely fine. Please take how much time you need.
So another class of examples are D3 branes probing Calabi-Yau threefold singularities. So these will give you 4D n equals to 1 SCFTs. The corresponding holographic dual lead to Sasaki-Einstein manifolds. For example, consider a Calabi-Yau threefold, which is Fermat type singularity, given by a hypersurface in C4, given by Zi to the power of AI, from I goes from 0 to 3 equal to 0. You bring D3 branes and put them at the point, you fill the space-time with D3 branes and put them at the position of the singularity at Zi equal to 0. That gives you CFT. Now, you could ask, what happens to Sasaki-Einstein manifold eigenvalues? Well, this turns out to be too difficult to compute. because we don't have the exact metric for Sasaki-Einstein manifold. So how do we do it? Well, it turns out that there are specific eigenvalues for which we can compute them. These are holomorphic eigenvalues, eigenfunctions. And these holomorphic eigenfunctions of these Sasaki-Einstein manifolds relate to chiral operators in the n equals to 1 theory. So chiral operators have spins or dimensions that are protected and are easier to compute, and we can use that to compute them. So therefore, if we can show that there is not a big bound for those eigenvalues, we have already shown that therefore at least some eigenvalues cannot be arbitrarily big. Not all eigenvalues can be arbitrarily big because some, namely the holomorphic ones, are not too high. So we use this as proxy for an upper bound for the first eigenvalue, even though the upper bound might be even smaller. So for the case of Fermat type, it turns out for all the AIs that you choose, the one which gives you the biggest gap is for the exponents to be 2, 3, 11, and 13. And this gives you the dimension of the first spin-2 operators, which is now in this case a chiral spin-2 operator. More what I mean is 202 in this example. So that's quite big, but anyhow, it's bounded. And no matter what other one you use, Fermat type, it cannot be bigger than this. For M2 branes probing Calabi-Yau fourfolds, this leads to 3D n equal to 2 theories. And so you take the M2 branes probing these singularities. And for example, if you consider Calabi-Yau fourfolds, which are given by hypersurfaces of the singularities of Fermat type, summation of Zi to the AI equals 0, it turns out that the biggest gap for holomorphic eigenvalues is achieved by the exponents given by 85, 83, 7, 3, and 2. And this gives you the first holomorphic eigenvalue corresponding to 6,975. Now, this is getting big, but still, the main thing I want to emphasize is that, first of all, this is upper bound for the gap. There could be lower ones. And secondly, it's a gap that it cannot be then do any better no matter what A you choose. So this is the upper bound in terms of what you can possibly achieve with the Fermat type Calabi-Yau. In fact, more generally for Calabi-Yau n-folds,
can't you get a lower bound in some way? I mean, is there a way of getting lower bounds as well?
Yes, there's a lower bound, for example, in these cases, which comes from the unitarity bound. For example, 3, 5, 7, you see these cases, the eigenvalues. So the lower bound is there, but we're interested in that whether you can push it up all the way to higher ones. The lower bound is easier to get in this case. The upper bound is what we're interested in.
But doesn't the lower bound mean that you already have a gap? I mean, you can't have.
No. What I mean by lower bound
gapless.
cannot be lower than 3, for example, here. In other words, the round sphere already gives you 3, the eigenvalue.
Oh, okay.
Yeah. Okay, so so the biggest gap for the corresponds for Calabi-Yau fourfold is this, but for any general Calabi-Yau n-fold, there's a procedure you can actually find what is the optimum exponents that you get to maximize this gap. And if you apply it for n equals to, for example, 2, you get the E8 case, you get 2, 3, and 5, the exponents of E8. So if you look at these exponents, you see the E8 case was 2, 3, 5, this is 2, 3, 11, 13, this is 2, 3, 7, 83, 85. And this sequence continues, and you can find how you compute. There's a general iterative procedure of how you find these exponents. Now, you might say, well, I have only looked at very specific type of Calabi-Yau, namely Fermat type singularities, but there are a huge number of others Calabi-Yaus, which are not even hypersurface, intersection of Calabi-Yaus, hypersurface, or other more complicated surfaces which are not given by Fermat type. What about those? It turns out that using the classification of regular singularities for Calabi-Yau threefolds, we have shown that for all of them, there's a universal upper bound on the first eigenvalue of the scalar Laplacian. So at least for the Calabi-Yau threefolds which have regular singularities, we have proven there is an upper bound. Now, there are also irregular singularities for Calabi-Yau, and for all the known irregular singularities, we have also proven there's upper bound. But since irregular singularities have not been classified completely, we cannot prove it for all Calabi-Yau period. But I think this is already a strong indication that that's the case. So therefore, we conjecture that the diameter of an n-dimensional Einstein manifold is bounded from below, and the first non-vanishing eigenvalue of scalar Laplacian bounded from above, where the bounds depends only on the dimension of the Einstein manifold. This is perhaps a surprising result, but this is basically underlies the analog of the statement that Suvrat was asking. There's no a priori conformal bootstrap problem of trying to get a big gap. This is the geometric analog of that statement, at least in this particular class, that why can't you make the diameter of Einstein manifold to be small? That's the question. There's no obvious reason, quote unquote, where we can explain it by or prove it, but this is what we are finding.
Hello.
Yes.
May I ask a question? So is there some trend in these upper bounds as you look at various singularities and various Calabi-Yau threefolds? Like, can you say where the upper bound is reached and so on?
Yes, so this class of examples shows you that the upper bounds are reached with an exceptional family. Similar to the gate case, similar to Monsters Moonshine, there's always the exceptional group is involved in some form or another. So therefore, yes, there's something exceptional about them. Doing it in a crazy way, like doing infinite order group or something, doesn't do a good job. If you want to get a big gap, you need something like the exceptional subgroups or something special, not the crazy infinite order.
But at least if you have a bigger rank group which you're modding out by, is that the statement that the upper bound reduces or something, or upper bound increases or something? I mean,
well, so there is the dimension for, so if you take the Sn and if you take n to infinity, the exponential eigenvalues could, so you see here the dimension of the first operator, the bound we're getting is get bigger and bigger. You see this here? So I had the 2002 and this is 6,975 and so on. So if you take a Calabi-Yau n-fold and you look at, but of course we don't know what's the relevance of that for conformal field theory, but if you take n-dimensional Calabi-Yau and take n to be large, you can make this first eigenvalue to be bigger and bigger and bigger. But for any given n, there is an upper bound. So in other words, this n can go exponentially. The first eigenvalue could be exponentially large in n, but no matter that, which n you choose will fix it.
Cumrun, there's no way to embed bigger and bigger products of exceptional groups as, I mean, for any fixed n, you can't like take, I know for the sphere and so on, yes, it's there's the E8 and so on, but as the spheres become bigger, the Einstein manifolds become bigger, you can't take very, very large numbers of products of exceptional.
Yeah. So let me explain. When I said exceptional, I didn't really mean exceptional group. Exceptional group was a kind of a simple example where you can actually have a quotient. This example here, let's just look at this one particular example, 2, 3, 11, and 13. This is not a quotient group of anything. This is not E8 or anything. This, I'm just saying this is extension of the 2, 3, 5 exponents of E8. But this is itself nothing to do a priori with E8. My main point was that the exponents are fixed and bounded, 2, 3, 11, and 13. Not that one exponent goes to infinity or anything. So there's an exceptional collection of numbers here. Making 11, 12 is not good, or 13 to be 15 is not good. This is the exception. That's what I mean. It's not a group, really. It's an exceptional number. Let me say it that way.
Right. But even in these higher dimensional spheres that you had earlier,
yes,
you can't sort of, there's no family. I mean, there are other infinite families, like you said, those probably don't work.
Yes. So what you do, the proof of that is that there are finite families. So for the finite families, you don't even waste your time because there's an upper bound. You only focus on infinite families.
So
and infinite families,
you can.
And the infinite families, the way you do the proof, the basic idea of the proof is that the infinite family, when you take the infinity out of the game, it reduces the space to a smaller space. Like in the case of the sphere, it squeezes it to an interval.
Right.
And that's
so
how
there's
you,
always
that's how
one diameter which is large.
Yes. So the infinite ones you trace like that, and the finite ones, some value, you don't care. As long as there's finite order, you just have a bound.
So you can't get in an infinite family of finite things.
Exactly.
What I mean is,
Exactly. Yes. If you had an infinite family of exceptional subgroup, then you could have had potentially a
that you
counterexample.
can't.
And that doesn't happen.
Great.
I have a question. Like,
Yes.
these are the cases where you can compute the eigenvalues, as you said, because eigenfunctions are holomorphic or something like that, right?
Yes.
So what about the cases where the eigenfunctions are not holomorphic?
But then you cannot do it.
I mean, there could exist a certain eigenfunctions which are not straightforward, but which could have eigenvalues going up to infinity, right? In principle,
well, first of all, even in these examples, most of the eigenvalues are not holomorphic. My main point here is eigenfunctions are not holomorphic. My main point is that there are eigenfunctions which are holomorphic in this case, and I can use those to get an upper bound. Now, you could say, well, there could be situations for which there are no holomorphic eigenfunctions, and that could also be the case. Yes, so I'm not claiming that we have proven it for all cases. We have proven it for all the Calabi singularities of the type I mentioned. We have proven it for all the sphere quotients and so forth. Sphere quotients are not holomorphic in general.
So you're saying the proof is not exhaustive?
The proof is for the classes I've just told you. Otherwise, we would not use the word conjecture here. The diameter of an n-dimensional Einstein manifold is bounded from below, and the first non-vanishing eigenvalue is bounded from above, where the bound depends on n, is motivated from all these series of examples, but we don't have a full proof. We don't have a proof. But I would say that it's surprising that that this is not true, and we would not have found an example among the vast classes that we have already studied. But then, it's still a conjecture. Now, from the worksheet perspective, probing singular Calabi-Yau leads to a parallel conjecture. In other words, you can translate this conjecture here. So if you apply this to the context of the Calabi-Yau, you can ask, okay, how does the string worksheet view this singularity? Well, it gives you some conformal field theory. In the case of Calabi-Yau, for example, it gives you an n equal to 2 conformal field theory, 2,2 superconformal field theory on the worksheet. So if you look at the degrees of freedom on the worksheet, this gives you some statement about the conformal field theory operators, because the mass of the states in the block gets related to the dimension of the operators on the worksheet theory also. So you can translate the conjecture that we just made to a statement about the 2D CFTs. So consider, in that case, we get a 2,2 superconformal field theory in 2 dimensions. Suppose you're interested in an n-dimensional Calabi-Yau. So typically what happens is that you get some conformal field theory with central charge less than n, c hat less than n, and the balance of the dimension to n is fixed by some linear dilaton, which is like a throat that we typically get when we have a brane probing a singularity. So we expect to have a linear dilaton background coupled to some internal conformal theory with a c hat less than n. Then the holomorphic eigenvalue gap not being too large in the bulk translates to a condition for the worksheet theory of the chiral fields of this 2,2 superconformal field theory, which says the following, that if you consider the conformal field theory, there are chiral operators whose charge Q also goes to 0 as c hat approaches n. That is, if you try to approach c hat towards n, these charges also approach 0, so that the dimensions cannot be pushed far enough up. In other words, Q over n minus c hat gives you the mass of the corresponding bulk operator. And for this to be bounded means that there is some operator for which this has a universal upper bound Cn, where Cn only depends on n and nothing else. This might sound surprising, but it's true in all the examples we know. So let Q be the chiral operator with the smallest R charge. That gives you the smallest dimension operator. And simple example I would say is the following. Take for example minimal models, 2,2 minimal models, and in that case the C hat approaches 1. So for the mth minimal model, the C hat is 1 minus 2 over m, and the smallest chiral operator has charge 1 over m. And so if you construct the corresponding dimension, the mass of the bulk operator is going to be proportional to 1 over m over 1 minus 1 minus 2 over m, because the central charge of the theory is 1 minus 2 over m. So if you plug it into this formula, you find that the m's cancel and you get 1/2. So as you take m to infinity, you cannot make this any bigger for the infinite series of that one. And for the minimal
What
model,
about Q, which is not 1 by m? For what about Q's which are not 1 by m but higher values?
no, those will give you more massive operators. What we want to get, what's the lightest operator? So the lightest
So what I'm saying is that if n and c hat, they tend to be the same, and you have a Q which is not related to m in any way, or say it's related to m in a different way, then you could have an eigenvalue which goes to infinity, right?
There's some problem with the internet.
Cumrun seems to have logged out.
Yeah,
Maybe there's some issue on his side.
yeah. Okay.
sorry, I got disconnected.
No problem. I was just wondering if everything's all right.
Yeah, I don't know why. So, but I'm assuming I just got disconnected.
Yeah.
You guys were connected, right?
Yes.
Okay,
yes.
sorry about that.
Yeah.
I don't know what.
No problem. Yeah.
So let me continue. So if you again host me, make me host.
Sure. Yeah. Just a second. Yeah, you should be able to share now.
Okay. Let me. That's sorry.
Yeah.
Okay. So do you see this?
Yes.
Yeah. So the answer to the question was that, of course, we get arbitrarily large eigenvalues. We're trying to make sure that there are also some light eigenvalues. Okay. So in fact, the biggest gap for the case of a minimum model is achieved not by the diagonal minimum model, but by the E8 minimum model, which is what we already mentioned. in that case, the corresponding gap becomes, this coefficient becomes 3, which is bigger than this 1/2. So that's the highest one we can do, and that's what it is. Now, one may think that this statement is rather restrictive and applies only to the cases of branes probing singularities and not to more complicated cases, because there are other ways to get holographic models. It doesn't have to be just the brane probing singularities. So, for example, there's a construction DGKT, which would be, which does not correspond just to probes of a singularity. There are more complicated elements in the story, fluxes of various types and so on. And indeed, if DGKT would correspond to a conformal theory dual, there will be a counterexample to the no gap conjecture that we made, that in fact, the exponent in this corresponding case will be lower than 1. So you can make the dimension of operators having arbitrarily large gap. Now, the arguments for construction of DGKT have two particular issues, actually a few issues. One is that they have singularities that they cannot typically resolve. And if you try to resolve them, there's not enough control about what geometry you get. Secondly, the exact geometry with the fluxes has not been studied. So the order of magnitude that people estimate for the corresponding eigenvalues is a ballpark estimate for the overall sizes of the manifold, which could be easily wrong, like this, like what I told you about the sphere and quotient thing. Even though you can cut down the one direction, make it small, another direction doesn't change size. So therefore, it may be highly anisotropic and it might be misleading. So we really need to know the precise metric, and this has not been done. And thirdly, if you look at the scaling of the central charge in the DGKT examples, if there were a conformal theory, the dual conformal theory, which would be a conformal theory in that case in 3 dimension, it will scale like n to the power of 9/2. And we don't have any examples of branes of any kind that we know in string theory, where if you increase just the number of branes, you will get anything higher than n cubed. And n cubed is for 5 branes, for instance. But this would have, if these constructions were correct, it would have given you n to the 9/2, which is bigger than n cubed. So anyhow, it's bizarre. But more than that, Cribiori et al. Used the DGKT constructions, extended it in some ways, and found by a series of duality examples to connect it to M theory with no other flux than overall flux, which corresponds to brane probing a singularity. So in other words, in that case, you would get in a dual description of DGKT in terms of Einstein manifolds. And in this case, again, if our conjecture applies, it will be ruling out these examples. So this would show that what the mistake would be in these cases is that the geometry is sufficiently anisotropic, which has not taken into account that fact, gives you the naive estimate doesn't work for the eigenvalues. So this is roughly the first half of my talk. Any questions?
I have one question, Cumrun. I mean, it's a general question. I mean, the proving of upper bounds for the spectra of operators, partial differential operators, usually uses what is called the Poincare inequalities. So is that the sort of technique that is used by you to estimate the upper bounds?
No. This is basically, let me say, the upper bounds that you mean, for example, here, what we found here, for example, how do we find the upper bounds here?
Yes.
We actually phrased it also in the physics language in our paper. This is basically the chiral operators, and whose dimension is protected by supersymmetry.
Oh, I see.
So it's very easy. You just say, oh, there's this charge, you just compute it. That's that easy.
I see. Okay.
So it's nothing.
Cumrun, I have one question.
Yeah.
Yes.
Yeah. So from practical viewpoint, I mean, suppose it's not possible to parametrically get a large bound, but suppose you get 1,000 times the ADS scale.
Yes.
Couldn't that be good enough for practical applications?
Yeah, for de Sitter, for example. Yeah, it could be. For example, KKLT do not get arbitrarily small bound, but they claim it's good for de Sitter application, which is the next thing I'm talking about. So you're right that for de Sitter, you don't need arbitrarily large gap, arbitrarily large separation of scale. Large enough you need.
Yeah.
Large enough you need. But of course, if you had arbitrary separation of scale, it would have made it easier, the construction of de Sitter, even though it's not strictly necessary. So KKLT does not does not say it's necessary, and they are trying to make it sufficiently scale separated for this to take place. And that's what I'm going to talk about now.
Thank you.
Yeah, so let's talk about the KKLT. KKLT is one of the few attempts for obtaining de Sitter, which is relatively viewed as one of the most promising attempts. And it has two basic steps. The step one is the use type 2B orientifold or F theory on elliptic Calabi fourfold with flux to obtain supersymmetric ADS with small lambda. So you get ADS 4 with a small value of the cosmological constant. That would be the first step. The second step would be to use anti-D3 branes at highly warped parts of the geometry to uplift the energy to positive cosmological constant, leading to de Sitter. It was typically believed that the first step was not necessarily too hard to do. To go on the second step, it was useful to make lambda really, really small, and people focused in the step one just to see if they can get a small lambda, so that the step two would be easier. But the step one was not actually critically reviewed in the sense that whether this is actually possible or not. And this is what I'm going to discuss here. We now argue why step one cannot be realized, which is the supersymmetric one. You see, the step one is more robust. It just uses supersymmetry, and we can use the arsenal of supersymmetric techniques we're familiar with to check whether or not this is possible. And that's what I'm going to talk about.
So here for small lambda, you mean parametrically small or just small?
I would, okay, good question. So they wanted they cannot be parametric small because these are coming from compact Calabi manifolds. So there's not infinite families, they're just finite. So it cannot be parametrically in that sense. They wanted to say lambda is much, much small. And in some sense, in the KKLT, they said 10 to the minus 5, 10 to the minus 6 in the Planck units. That's what they thought is good enough, for example, for them, at least. Here, what I would argue is actually worse than that. I would argue that no matter how small you can make lambda, no matter which Calabi you choose, your effective field theory breaks down. That you cannot have an effective field theory with small lambda. That's what I want to argue. That the lambda, the corresponding lambda, is always in a regime that your effective field theory is untrustable, therefore you cannot even proceed. You cannot use Einstein gravity to talk about it anymore. That's what I want to talk about. So the value of lambda would be irrelevant for me.
I see. But you could still use full string theory in principle.
Sorry?
You could still use full string theory to analyze this in principle?
In principle, one can use, yeah. In principle, you can, the solution might exist in some form, but we have no control. These kind of arguments don't apply anymore. That's right. So we don't say that these vacuum cannot be constructed, period. But no matter what you do, it's not going to be a Einstein gravity. You have to do more than Einstein gravity. Exactly. That's what we want to talk. So therefore, the whether or not it exists does not follow from this path. That's what I'm trying to say. So step one means, so more precisely, I'm saying step one is not under effective field theory control. That's a more precise statement.
Okay. Thank you.
So start with F theory on elliptic fourfold, or which is equivalent to a Calabi threefold orientifold, Calabi threefold with orientifold action. Now you take in this context, there's a tadpole condition which fixes in the context of the Calabi fourfold, the Euler characteristic of the Calabi fourfold x4 divided by 24 is given by the number of D3 branes that you need to put, plus amount of flux you're putting, given by the Ramond flux, F3 times the wedged with the Neveu-Short flux H3, integrated over the corresponding Calabi. And in the orientifold limit, this is can be viewed, the Euler characteristic can also be related to the number of orientifold 3 planes plus the Euler characteristic of the orientifold 7 planes. So you can formulate this whole equation purely in terms of the orientifold description, or if you want more fancy version, this is the more fancy version in the F theory language. Now, what we want to do in order to get the biggest amount of the smallest amount of lambda is to make the flux as big as possible, like large N situation. And that could be done if you get rid of the number of D3 branes, and that's in the context of KKLT, what would be the best in terms of trying to get the smallest lambda. So let's assume we can set the T3 brane to 0 with no problem with the fractional ones quantization here. So let's just suppose we can do that and we get rid of it altogether. So here we get the relation, therefore, between F wedge H in terms of the Euler axis of the Calabi-Yau fourfold. So this leads to an effective 4D theory. The existence of the flux gives you a superpotential in the effective 4D n equals to 1 theory, which the superpotential gives you the effective potential V, which gives you the usual formula for the potential dictated by the superpotential and the corresponding Kähler metric. In this case, the W will be 4 wedge omega 4 in the language of the fourfold. In other words, you can think about you can unify the 3-form fluxes into a 4-form flux in the language of M theory, and the corresponding superpotential can be viewed in this form, or you can translate that in the Calabi-Yau threefold language as G3, which is F3 minus tau, the coupling constant of type 2b, times H3, wedged with the holomorphic 3-form of Calabi-Yau, and this would be the corresponding superpotential. If we define the quantity absolute value of Z, which is e to the k over 2 times W, so k is the corresponding Kähler potential, which gives you the corresponding Kähler metric in the n equals to 1 effective theory. And if you look for ADS vacua, so the ADS vacua are a situation where you're looking for DIW is 0, but W is not 0. This is equivalent to solving critical points of this function. So if you look at critical points of this function, that's equivalent to solving this equation. Now, this looks very much like an attractor equation. In fact, this was noted that's an attractor-like equation in old paper by, well, Sviatek et al. Had already studied this equation. Notice that this is one way to rephrase these ADS vacua, and Kalash drew attention to the fact that this looks like an attractor equation after the KKLT paper. So she was basically pointing out that the KKLT situation is in some sense like going to an attractor, finding solution to KKLT is like going to an attractor fixed point. And this attractor fixed point is related to a would-be central charge of this W, which after all is related to this fluxes caused by this 4-form flux in the M theory language, which would be in terms of M5 brane or the corresponding objects in the reduced object in the kinetics of type 2b. So so now what do we learn from here? Well, it is very much looks like attractor equation for black holes, for example. Just let's review that first to get an insight. If you consider type 2b on a Calabi-Yau threefold and consider D3 brane wrapping 3 cycles, there is a central charge corresponding to the mass of the black hole in the Einstein frame, which is given by the integral of the holomorphic 3-form corresponding to the cycle that the 3 brane wraps, normalized, so that basically going to the Einstein frame means this normalization. And this gives you a mass of the black hole. And the attractor value for the complex structure of Calabi-Yau is exactly going to the critical point, the minimum of this black hole mass. Whereas you minimize the mass of the black hole, and that gives you the attractor value. And this equation is very much in the same spirit, where now this omega is integrated over something which looks like a 4 cycle if you translate this to a dual 4 cycle. We can, in principle, consider ADS in 4 dimensions. That is the case directly related to KKLT, or 3 dimensions. In other words, you can think of going down 1 dimension and doing the M theory on the Calabi-Yau fourfold case by the duality between F theory and M theory. The arguments of KKLT, the statistical argument, apply equally well to both cases. So if one has an issue, the other one has an issue, and vice versa. I will study both of these. And in fact, geometrically, it's easier and more unified to talk about the M theory case, because it's one object to talk about. We don't have to split it to F and Ramond and Neveu-Shor's flux and this and that. And it's more general in some sense. So I will mostly think about it as if I'm talking about the 3D case, namely M theory and Calabi-Yau fourfold, but it's easy applies to F theory on elliptic fourfold. Now, how do we interpret the attractor equation? Well, just like the usual attractor equation, we always have to think about what gives rise to this flux. So if you take M5 branes wrapping a 4 cycle in the M theory context, condition for supersymmetry requires it to be special Lagrangian. Namely, if you take a M5 brane wrapped around a Lagrangian submanifold, for which the Kähler form restricted to it is 0, if you also insist that the imaginary part of the holomorphic 4 form with a suitable chase of an overall phase, if the imaginary part is 0, then you find that this is a special Lagrangian submanifold, and this is a preserved half-the supersymmetry. In fact, it turns out that this is precisely the dual condition to the fluxes that the M theory have to satisfy, namely, there should be a self-dual form, 4 form, and primitive. The primitivity of the form gets related to this condition, and the self-duality corresponds to this condition. And so therefore, these conditions on the brane are exactly the same conditions that you need on the flux from the bulk perspective as well. So therefore, this suggests the following picture for realizing this holographic setup. So
sorry,
for example, having...
Hi, could I please ask one small question here?
Yes.
This condition for these M5 branes wrapping a C4, so normally this e to the k over 2 W, this mod Z that you call, that's usually the gravitational mass, right? So is it that one is equating the gravitational mass with the tension of these M5 branes wrapping a C4?
E to the k, no, it's more, I mean, it depends on W and all that. So it depends on more data. It's not just the mass. It's a tension. The W is roughly the tension of this domain wall. The W should be viewed as tension of the domain walls. But perhaps I should explain this and maybe it becomes more clear what I mean. So if you look at this picture here, so imagine we are doing this in 3 dimensions now because we have gone on M theory and Calabi-Yau fourfold. Imagine that on the left-hand side, imagine you have, if you want to solve the condition that the number of D3 brane in this case becomes M2 branes, is the Euler characteristic of Calabi over 24 with no flux. This is one perfectly fine solution to the Tadpole condition. But now you can find a new solution to the Tadpole condition, which is converts all of these branes into fluxes. So you can put all of them into flux by doing the following trick, namely, take an M5 brane, which so you can have an M2 brane which ends on M5 branes, which wraps a particular 4 cycle, such that the corresponding 4 cycle 4 form gives you G4, where G4 equals to pi over 24. So you put this M5 brane wrapped around the 4 cycle to generate it. Notice that the M5 brane wrapped around a 4 cycle in a Calabi-Yau gives you a 1 + 1 dimensional object in 2 + 1 dimensions, so it's a domain wall. So you have a domain wall, and after that, you generate, you can ask what equations do they satisfy. Well, then you write down the equations that you generate, and you exactly get that as you go in the large Z direction, you find exactly the flow equation that's familiar in the context of a attractor equation, where you find that the values of the moduli settle to the critical points of Z. And at the critical points, this metric becomes an anti-de Sitter metric far away. So therefore, this is naturally interpretable as the domain wall is creating the ADS dual description. So as is usual in holography, the ADS bulk is dual to one lower dimensional brane supporting the flux. So therefore, this naturally suggests that in the first step, the ADS holographic dual to this ADS in the perturbative 2B can be viewed as D5 or NS5 branes wrapping 3 cycles, giving to 2 + 1 dimensional domain walls, or in the M5 brane, excuse me, in the M theory language, to M5 branes wrapping around the special Lagrangian 4 manifold, SLAG4 of Calabi-Yau fourfold. This point is not new. This has already been made by Silverstein shortly after the KKLT paper. She suggested indeed that these D5 and S5 branes wrapping these special Lagrangian submanifold should give rise to the dual description. Okay, now, so whatever the conformal theory is, the L of ADS to the squared power should be the central charge. That's just the relation between the length of ADS and the central charge of the theory. In the A3 case, in the 3D case, it should be the length of ADS is related to the central charge of the corresponding M5 brane wrap. Now, we will now show that this number, these central charges, are bounded by the Euler axis of Calabi-Yau. That's the first step we wanted. Any questions before I do that? So in other words, I want to show that the length scale of ADS cannot be made arbitrarily large. That's not that surprising because there's a tadpole condition, and I'm saying that that is related to the chi of the Calabi-Yau, the Euler axis of the Calabi-Yau, which sets the size for the scale. So in fact, before I do this, I want to give you 3 parallel cases. One of them is already studied, and this is considering M theory on the background given by ADS3 times S2 times the Calabi-Yau 3-fold. In other words, instead of the Calabi-Yau 4-fold, I could consider S2 times the Calabi-Yau 3-fold, and this was studied by MSW. You consider an M5 brane wrapping on holomorphic 4 cycles of a Calabi-Yau 3-fold, and this gives rise to a string which is holographically dual to this geometry, which has 0,4 supersymmetry. This is similar to what we want, except that in this case, the S2 times X3, we are replacing it by an X4, and the holomorphic 4 cycle is replaced by a special Lagrangian 4 cycle. The next case is you take ADS times the Calabi-Yau 4-fold, but now wrap M5 brane around holomorphic 4 cycles of a Calabi-Yau 4-fold. This gives rise to a 0,2 supersymmetry in 2D. This is a perfectly fine situation, but it's not the one which we are necessarily interested because it doesn't come from 4D. It's an M theory construction and gives you another conformal theory. The one we are really interested in is case C, which is ADS3 times X4, where the M5 brane is wrapped around special Lagrangian 4 cycles, which gives you dual to 2D 1,1 supersymmetric theories. But let's first review the easier cases for A and B to gain insights, and then we apply it to case C. The case is
before
yes?
you go on. So are you saying that the Calabi-Yau manifolds can't be smaller than a certain size?
Well, that's not what I'm saying, because it depends on how you want to phrase it. If you want to say that the minimum point, what particular flux they will have, yes, they would be related to that. But the question is, how big is the Calabi-Yau? That's correct. In other words, if you want to view it that way, I'm saying that there's a bound on how big LADS is. That means by the correspondence with the fact that the scale of Calabi-Yau is not separated, means the Calabi-Yau cannot be too big either.
Yeah. So if
but that's not. I'm not emphasizing that aspect because I'm not using it.
No, if the size of the Calabi-Yau can't be smaller than a certain size, then you would have the problem of KK modes appearing, which would kind of invalidate the analysis. I mean, if you're considering realistic theories such as the theory of nature, for instance, if you want to consider that KKLT gives rise to the theory of nature, then you would have a problem, right?
You could have a problem, but since that's a totally different thing, we have positive cosmological constant and all that. Let me not make my life more complicated by getting that. But yes, in the sense that if you could have made the Calabi-Yau arbitrarily big, that would be corresponding to ADS being arbitrarily big, and that would have been good for the KKLT scenario. I'm saying no, there's a bound on how you can make the ADS big, and therefore the KK modes are also bounded similarly. So let me talk about the case A here first, which is very easy, because here you can actually find the dual conformal field theory central charges easily using anomaly inflow. In other words, anomaly inflow tells you what's the left and right central charges simply by using the anomaly inflow argument for 0,4 theory, where here the C4 is the class of the 4 cycle that the M5 brane is wrapping, and the central charges scales like C4 cubed, triple intersection of that 4 cycle, plus second Chern class of Calabi-Yau times C4. the left, and similarly for the right, left and right. For the case B, similarly, anomaly inflow again fixes the central charges. Now it goes like C4 squared and some linear term in C4. Notice that for large C4, this scales cube of C4, and this scales like square of C4. It is not surprising that this goes like cube and square for the case of 4 cycles wrapping the Calabi-Yau 3-fold or 4 cycles wrapping Calabi-Yau 4-folds. Why is that? Well, the reason is that suppose they did not intersect. Suppose the intersection were 0. Well, then you would separate them. You would separate the cycles. You can take n copies of a cycle and separate them, and the central charge would typically add. However, if it is not separable, then there will be some extra degrees of freedom localized at the points they intersect, and there will be some universal constant times the number of intersection points that they give, so some local degrees of freedom coming from the points they intersect. So it's natural to expect for large C4, they go like the intersections of them, which goes like C4 cubed for the holomorphic ones in the Calabi-Yau 3-fold case, and the 4-fold case goes like C4 squared, because you need a pair of them intersecting in Calabi-Yau 4-fold. So this is natural and it's explained. Now let's go to the case we are really interested in, which is M5 range wrapped on special Lagrangian 4 cycles. If you can consider the UV degrees of freedom on the corresponding special Lagrangian 4 cycles, you have a 4 manifold inside the Calabi-Yau. The Betty numbers I'm calling B1 and B2 and so forth. You find that the 1,1 theory in the UV has central charges given by 1 plus the number of anti-self dual 2 forms, B2 minus, plus B1, and then the number of right degrees of freedom is 1 plus B2 positive self-dual 2 forms plus B1, first Betty number. And this gives rise to central charges, which is 3 halves in left and in right. So if you add the central charges of the left and right, you put these together, you get this is given by 3 halves times chi plus 4 times B1. Now, in the 4 cycles, which is special Lagrangian, locally inside the Calabi-Yau, just because of the Calabi-Yau conditions, have the geometry cotangent of 4 cycle like this. So the and there's an easy theorem, topology theorem, says that once you have such a geometry, the self-intersection of this 4 cycle inside this local geometry is related to its Euler characteristic of this 4 cycle. So this means that the C left plus C right is given by left L4 dot L4, the intersection of these 2 4 cycles, plus 4B1. And this is in accord with the expectation that this grows like L4 times L4. And we don't expect B1 to grow faster than L4 times L4 because of the argument I gave in terms of the fact that when you move them away, you should get coming degrees of freedom from the intersection points of L4. So in the local Calabi-Yau manifolds, L4 times L4 is equal to Euler characteristic of as I said, the Euler characteristic of the L4 is a self-intersection, but the tadpole condition, there's the L4 times L4 is related to the G4 wedge G squared, and therefore this, because this is the class where the 5 brane wraps around, but the tadpole condition says this should be less than the Euler characteristic of the full Calabi-Yau, which tells you that the ultraviolet central charge is less than order 1 number, depends on what's the coefficient of that in the central charge, times the Euler characteristic of the Calabi-Yau. So, and similarly for F theory case, we obtain a similar formula that the central charge is less than some constant times the Euler characteristic of elliptic 4-fold export. So this gives rise to the fact that ADS is length scale is less than the Euler characteristic of the Calabi-Yau in both cases. One is square, one is not square because of the usual formula relating the radius of ADS to the corresponding central charges in the dual conformal theory. However, the effective field theory, when you have many light degrees of freedom, changes. Namely, if you have a huge Euler characteristic for the Calabi-Yau, then you have a huge number of light modes, massless modes in the context of Calabi-Yau, and therefore the effective Planck scale, which is what's called the species scale, changes, and it becomes bigger than order 1 in Planck units. Indeed, it becomes, in the 3-dimensional case, becomes bigger than the number of massless modes, which is chi, Euler characteristic of the Calabi-Yau, And in the case of the 4D case, the species scale squared is bigger than the Euler characteristic of the Calabi-Yau. So in other words, you can make the Euler characteristic bigger and bigger and hope to get the smaller value, bigger and bigger value of ADS. But at the same time, the breakdown of the effective theory is triggered, but not by the Planck scale, but by a bigger scale. So the cutoff of the theory is not as small as Planck, but bigger. And indeed, the cutoff of the theory, the length scale cutoff of the theory is bigger, as we can see from the ADS scale. So the effective field theory breaks down. That's the point I wanted to make. So even if one ignores the issue with species scale, it turns out for the cosmological constants that you get, these don't get such a small cosmological constant. For example, in the context of orientifolds, you can show that the biggest you can make the Euler characteristic of the Calabi over 24 is 252. And this will tell you that the lambda that you get is bigger than 10 to the minus 2. So now there has been papers like last year by Demirtas et al., where they claim to have obtained the first step with very small values of the cosmological constant of order 10 to the minus 120 or whatever, with a negative sign and all that. Looks pretty good. But what those papers did, they did not quite find the Kähler potential. They gave some heuristic argument why the Kähler potential does not mess up their construction. However, if you look at the choice of fluxes that they chose, you can ask, what does it translate to the kind of branes? And what they did in this language, is in the mirror language to what I'm talking about, is that they chose holomorphic and anti-holomorphic cycles so that the net effective area was 0 at the expense of breaking supersymmetry. In other words, even though at the level of fluxes, they would preserve supersymmetry, at the level of Kähler potential, they cannot preserve supersymmetry in those contexts. This is somewhat similar to the Calabi-Yau case, that if you choose some specific direction of fluxes, there are no supersymmetric BPS objects in that path, and this will have a similar fate. The examples that they would have hoped to exist. Now, note that here we have used the conventional notion of holography where we replace fluxes by the branes leading to it. This is the case in all the known examples in string theory, and the idea that there could be other holographic duals, even though we have identified the right brane within the right string theory with the correct amount of supersymmetry, which seems rather strange. So this doesn't seem to be to us a good loophole to try to get out of it. And indeed, it's not surprising that Silverstein already conjectured that these are the corresponding holographic dual objects. So this is similar to ask. So if one says, no, there might be other holographic dual, it's somewhat similar to asking in the context of BPS black holes, maybe D branes are not the right objects. Maybe there are other objects which have much bigger entropy than these, and then it will not give you the Bekenstein-Hawking entropy, for example. But I think we by now know the relevant objects in string theory, especially in supersymmetric cases, to have confidence in our understanding. So if conventional holography applies to this case, which we have assumed, then KKLT cannot be under effective field theory control. So let me conclude right on time, hopefully, that scale separation does not seem to be possible to achieve in ADS context. At least in all the known cases we have examined, it seems to be a problem. And assuming conventional holography, KKLT scenario is obstructed, and suggests that if we should be looking in other corners of landscape or have more other techniques to have more control of these corners if you are to obtain quasi-de Sitter vacuum. Thank you.
Thank you. Hi, sorry, I think I was on mute. I was just saying, let's thank Cumrun for a wonderful talk.
Thank you.
Yeah, yeah. Any questions?
What is the final statement about KKLT that you are making?
KKLT is not under in the regime that one wants for small chi, for large chi or small value of lambda, is not under effective field theory control. It doesn't mean that there is no ADS vacuum. It just means it's not describable in the way KKLT did.
Do one have a 10-dimensional effective field theory description?
Sorry?
Can one have a 10-dimensional effective field theory description?
Can one have another effective field theory description?
10-dimensional description.
10-dimensional, no. the effective, well, okay. When I say I'm saying Einstein gravity would fail, namely the effective description is breaking down, namely the ADS scale. That's Einstein description. You can read that as 10-dimensional. It's not the 10-dimensional aspect. I'm saying that the curvature, it's like saying that I'm having a background ADS curvature, which is bigger than Planck curvature.
I see.
We don't trust that solution. That's all they are doing. The effective scale is Planckian curvature. So if you want to say, yeah, that's what they are doing. Planckian curvature.
Sorry, could you just repeat again the statement about the Cornell group construction when you said that the scalar potential part breaks supersymmetry?
Yes, I can explain that. Let me explain that. So let me take a very simple example so that we all know what we're describing. Take a Calabi threefold for simplicity, and take a P1 times P1 inside the Calabi threefold. You can wrap, for example, M2 branes around P1s, holomorphic M2 branes with one, and another holomorphic M2 branes around the other one. And the mass will be the sum of them, right? It depends on which directions we pick. But you can also do something else. You can choose M2 branes wrapped around one P1 and anti-M2 branes wrapped around the other P1. Right? In this case, the naive central charge could be made to be 0. Right? Because it's A minus A prime. But there is no BPS object in that class. So there's a direction in the fluxes where there's no BPS state. There's no supersymmetric object. The supersymmetric object is in a cone, which is given by positive combination of these P1s, not one positive, one negative. So the kind of construction these guys did was choosing positive in one direction and negative in the other in order to get the sum of them to be very close to 0. And hoping that that would be supersymmetric.
So the hoping because they would satisfy the I mean, so they satisfy the in the superpotential. It's very it satisfies the supersymmetric conditions from the superpotential, but it's not. So that's why that's the basis for that hope. I mean, when you say hoping it,
Exactly.
Yeah.
So in other words, they couldn't compute the Kähler potential, which you need if you want to claim to have ADS vacuum, which needs the Kähler metric, which is very hard to compute. They gave heuristic arguments to try to motivate why that would be still okay, but that's the problem.
Okay.
You know, from our perspective is that there is no holographic object dual to it. There's no supersymmetric holographic brane with those charges. That's what we're saying.
Okay.
And we told this to them, and they would say, well, how do you know holography is given by branes? That you know. So that's basically that they're hoping for non-conventional holography that we don't have any idea. So they agree that the holography, the usual holography will give them a problem.
Are you essentially saying that KKLT doesn't work?
KKLT doesn't work if you assume the usual notion of holography. If you assume a standard holography, it doesn't work. So I'm using holography in a strong way.
Okay.
So this non-conventional holography would have had to have a construction which involves flux. I mean, the fluxes are somehow. So you are trying to say that you could have viewed it instead of the flux configuration, a corresponding configuration of D branes, but they are saying that there would be no way in which you could construct that flux that flux configuration with a configuration of D3 or the corresponding D branes.
Right. The kind of things they say is that it cannot be the usual conventional brane over conventional manifolds. They say maybe it's the brane wrapped around the whole manifold and manifold has shrunk to 0 size and this and that. So in other words, the kind of things they say is that it doesn't work the naive way we are expecting that to work in all cases that we do know. And they don't have any construction. They just say we don't know. But okay. This tells you that the issue is. In fact, I should say that there's an easier way. Let me explain why KKLT doesn't work in a one line, so that you see it's not really a big deal to explain it. So let me try to explain it in a better way, perhaps. Let me share my screen again. Do you see my screen here?
Yeah.
Yes.
So let me go to a particular easy way to explain why it doesn't work. So look at this formula. Look at this formula here, the Tadpole condition. And let's set the number of D3 brane to 0. Now, you say, okay, what do we want to do? We want to have to make these fluxes to be big in order to get small lambda, right? That's obvious. So you get bigger and bigger. Of course, this is bounded by chi. Now, if you rescale the fluxes by some factor, the number of branes are rescaled by that same factor. So if you have 1 unit of F, you have 1 unit of brane. So if you call the number of branes n, this tells you that n squared factors like chi. And these are made of D5 brane and NS5 branes, whose central charge goes like n squared. So that means n squared, which is the central charge, goes like chi. That's all. So this is basically telling you that just like the usual orientifold, which you have a upper bound of how much branes you can put, like when you take orientifold, you cannot put too many branes, like in SO32, you have to put only 32 branes to cancel the tadpole. This same condition tells you cannot put too many branes, and the biggest you can put is at most as much as equal to chi, such that n squared is over the chi. So it's not surprising. It's very natural that you cannot achieve holography in a compact Calabi-Yau the way they want to be too big, and therefore, it's related to the Euler case of Calabi-Yau and central charge being related to the Calabi-Yau in the way I just said here. If the central charge is bounded by the Calabi-Yau, then the rest of it follows from the fact that the species scale is the other way, and so therefore the ADS scale is less than species. So it's really a one-liner. It's a very simple argument. So in some sense, they should not have expected this to exist.
Yeah, basically you're saying that in a compact Calabi-Yau, you'd have these absolute upper bounds on just the number of branes. And
if you convert the fluxes to the branes cannot give you too big. Exactly. The branes cannot be, the fluxes converted to brane, which is holography, cannot give you a big central charge. That's the statement. Yeah. That's what I mean by conventional holography.
Okay. Thanks, Cumrun.
Are there any other questions? If not, let's thank Cumrun again for a great talk.
Thank you.
Thank you for making the time. Yeah.
Thank you. Well, it was a pleasure, and I really enjoyed the very interactive audience you have. Thank you.
Okay.
Bye-bye.
Bye.
Yeah.
See
Bye.
you.
See everybody.